Okay, everybody, this is the last session for today. Celeste Betancur is going to deliver a workshop on the talk that she gave this morning. This will be the last presentation today. So please enjoy. Thank you.
Well, hi again. I'm going to try to well, as David, I have a lot of examples we could try to go around. My plan in general terms is to start with ChucK as a language, because I know there's some people never heard about this language before. So I'm going to start with a very simple example of how to make a sound and a rhythm. And then I'm going to try to jump into the new features of the language. So the first example is going to be like 5 minutes, very, very short and fast, just for the new ones. Then I'm going to jump into the new features of the language, which are the ones that I know no one knows because are just released. And has been released in the last few weeks, months, like operator overloading, which I think is awesome and cool. I'm going to explain a simple example on our new feature collector, which is a very powerful thing to extract MIR features. You just replace something and then you have a lot of information with 15 lines of code. And then my plan after that would be doing the HMM simple example using Markov chains, like from comparing hard coding the rhythm and then using the Markov chain and then showing that it's very easy. Finally, there's more examples I can show. One using the ChucK library. That's not essential, but we can go and touch that. And also there's more examples you can find in the repo. So let me show you. The code is in this webpage. It's my GitHub. The repo is PAW workshop. And you will find this folder with these files I have here. It's a folder with 6 audio samples and some ChucK code. This is the GitHub. I'm going to show you again. Yeah, don't worry. So it's this one. It's github.com/Celeste Betancur /PAW and then worship, like that. We're going to need you to have a very updated version of ChucK, because if you're using an old one, probably some of the features I'm going to show you will not work. Like operator overload it's in one of the newest versions. That should be, if you install ChucK in the last month, I think it should work. It's probably the last one. But we can have a test. Let's see. Okay, so in this same repo, in the repository, there's some, in the README file right here, down, is the reference for everything. So if you need to install ChucK, the first link that's here will take you to this page. And then that page, you can see this link that says download ChucK. The Mac installer that's on the page, it's 15018. That should be enough. Yeah. We can use the web ChucK if, well, that's a very good option. If you don't want to install anything, you can simply go here. So there's another link here that says web ChucK. And you hit the second one, and it will take you to this page. That should also work. Yes, that's one of the good things about this. Like we are thinking all this ChucK stuff as a very educational tool. So that's why this should work, and it shouldn't be a problem. It has CHI, it has operator overload, so you don't need to install anything. You just go here and it will work.
Some years ago there was something called PAW, which was
Yeah, it.
not my name.
No. I think it's Roman's idea, but it's a good thing because we have someone to blame about that, and it's on the room right now. Well, actually, 2 people in this room are to blame about that. It should work. It was working, but then after some updates.
There's a GitHub for it now. It's a dedicated repository, so karma/.
Yeah, but I tried to install today and it wouldn't.
Maybe on Linux. It should work on Mac.
Yeah, but for me, Linux today, it didn't work. Yeah, but so it should work. If it doesn't work, blame David Brown. Talk to David Brown. He's in charge of that little thing, which is amazing. I forgot to talk about that in the morning because ChucK is very good for control. So you can have control of what's going to happen, triggers, turn on, turn off, automations, but not good or not good for describing DSPs. It's more complicated than Faust. So it's good to have FOC because that way you can describe your DSP in Faust and just use the object and control it from ChucK, which is a very powerful thing because then you have the best of both worlds. Like have a sequencer that's on ChucK side that triggers Faust synthesizers, and that's freaking awesome. But we need well, I think that will not work yet in the WebChuck version because WebChuck doesn't allow you to upload chuggings until last week. We get to compile the WASM file, so probably the next version that's going to be ChucK 1.6 is going to have the FAUC plugin on the web. Yeah. Okay, so is anyone having, like, it shouldn't be any problem. If you want to install ChucK, you could just go install it. If you don't want to do that, just go to this page. Yeah, that's in the README file. And you can just try everything here. Okay, so let's start with something. I'm going to show you just the example. Okay, so I think we're not going to touch this part. This was the example I showed you in video this morning. This mosaic code. It's 2 files. The first file is the mosaic extraction feature. So you just put any .wav file.
Sorry.
Yeah.
So the name is not ChucK, it's mini article?
Mini article is the IDE.
Okay. So the application, okay, but when you install it, if you look into your application folder, you won't see ChucK.
You will see mini article.
Yeah.
Yes. Yeah, at least for, Yeah. At least for Macs and Windows. Linux will not have mini article, but ChucK, because, well, it's different. But yeah, you will see something called mini article. Yes. So feel free to interrupt me whenever you want. So I'm not going to touch this example, but you're going to have it just if you want to play with those. So this mosaic extract will extract features of any WAP file, any file you want, and it will extract any features you want. I'm going to explain this in a bit, but like right now, as you can see,
What file must be mono or can be stereo?
it could be any, mono or stereo. So I'm just going to go very fast through this example because I'm not going to touch it in the workshop. So this part, we are going to be touching this part, is the feature extraction. So ChucK has a very powerful MB library for doing audio extraction now, and we're going to make it bigger in the next month. In this case, it's extracting the centroid, the spectral flux, RMS, the coefficients of the frequency, and the spectral chroma. So it's extracting those features and then is making a file with those features. And then with the other file that's here, mosaic synth microphone, it will play as the video you saw, like G1 making Screamo in the morning. So you just use this one to extract the features, and then you use this one to play with, and you will get something like this. I'm just going to show the example running, but it's the same code you're going to have. So I'm going to turn on my microphone. Hey. Hi. Woo-hoo. Well, this is a file that's doing this, but if you just put any other file, it will make a different mosaic, which is a different synthesizer kind of stuff. So that's just for showing you. You're going to have that code. It's in this repository, but I'm not going to explain it in deepness. It's just there if you want to play with this part. Because this one is more complicated for like in ChucK stuff. And I know some of you have never used ChucK before. So that's why I'm going to start with some basics. So from scratch, we're going to make a very run, like 2-minute example of how to make ChucK do stuff. First thing, let's create sound. So sine oscillator is the abstraction for that. You just put a name. In my case, it's going to be called Celeste, but it could be anything. And you connect that. This is the ChucK operator, which is very overloaded. It works for everything. In this case, it's like a connector, like a cable to the DAC. The abstraction for the digital analog converter. And then easy, you just type an amount of time. Second to now. That will be the Hello World ChucK program. It's a very simple program that will speed a sinusoidal oscillator for 1 second. So you hit start web ChucK, it will say here web ChucK's ready, then you hit play. My audio is not coming from the, let me see something here. I heard some beep. Yeah, well, that's the hello world. Yeah, great. is this? Okay, this is the hello world. So I was explaining to you this morning that this language compared to every other language in the world, like I think this is the most special thing of this language is this kind of sentence, like a statement, because it's very specific of the amount of samples you want. Like this program is explicitly saying, give me sample rate at the level that you have your setup, your sample rate, it will spit that amount of samples. So 1 second in this computer is 48,000. It's going to spit exactly 48,000 samples, and then it's going to stop. And that's great because what I was saying, it's very useful for controlling stuff. I think everyone's did this fine, so now I'm going to make a variation very fast. I'm going to just add a frequency. This is just a very kindly introduction to the language. And then we just do 880, and I don't know, just copy paste, and then 666. Something like that, and then you hit play again. I was just copy pasting things. You can just put any frequency you want. That frequency is in hertz. Well done. Now you know how to program in ChucK. Everything else in ChucK works almost like every language in the family of C or Java. Almost the same thing, like C++, kind of Java, kind of JavaScript when it was more not functional, but like the older versions, kind of C. Everything works the same. So just a very fast. You can do a while loop. You can do a do repeat. You can do the repeat. You can do a for loop. And everything is like syntactically it's exactly like C++, semicolons. Well, I think you have the idea. So this was the first example, and we know how this works now. So I'm going to jump into more deep stuff because if not, we're going to be stuck in the simple things. I could keep this thing here. What about the analyzers? Because that's what we want to do in this workshop. Everything in ChucK could be connected like this if it's a signal, but then if it's an analyzer, we have another operator. And this operator is this and this. This is the operator for analyzers. So we're going to try to analyze this a simple code. It could be a sinusoidal thing. So what I'm going to do is, instead of doing this connection here, I'm going to connect this to an FFT object. And then I'm going to connect that to any analyzer. So if you go to the page, I was in my repository, you go to the reference. The ChucK reference is pretty well documented since this year. It was awful before, but now we made a great job. Like, we have examples and many other stuff. So we have the unit analyzers here. So you can just pick anything you want. I'm going to just, for the purpose of explanation, just use the centroid. So I'm gonna do the FFT And then I'm going to up ChucK. This is the operator that's named up ChucK, a centroid. I'm going to call that cen, maybe. And then I can connect this to the black hole, which is like an abstraction again of a DAC that doesn't make sound. Because we just want to analyze this. We don't want to hear anything. Like this was the old way of doing it, and it was good. But now we have this new thing that will simplify a lot this. It's called feature collector. Am I wrong here? Yeah, that's the name. Oh yeah, I know what's the problem here. Collector. Okay, and let's call this like this. So this new feature will help us with a lot of stuff. So after doing this, you can call this function up ChucK. This is the function that's like run. And then we can figure out using this function how many features, the number of dimensions of the extraction we're using, which is important because maybe you don't know how many outputs is going to give you the centroid. Maybe you don't know. So you're going to use this. Everything is on the code I sent you. So we are using this example. If you need to see where are we working, we are in this example that says hmm.ck. That's the one that we are using as reference. Okay, so I'm going to print that number just to see if it's working. This is the print statement in ChucK. It's called the hack operator. And you can run that. Okay, so you see in the console here, I'm pointing there, the amount of the dimensionality of my analysis is 1. That means centroid is just giving you one number, which makes sense if you know what's the centroid. But it could be different because if you're extracting coefficients like MFCCs, you can customize the amount of coefficients you want to extract. It could be 56, for example, and this number will be 56. If you extract other things, there's a lot of things here. So RMS, for example, will give you 1. Chroma will give you 12 dimensions. And each analyzer is going to give you different dimensionality. So this thing is very easy right now because now you have the number. Okay. Now, what we're going to do is to finish, like I'm going to go back here to my example. We're going to set the window. So I'm setting the window size for the analysis, the window type, and the size of the FFT. Okay, again, if you need to see where I'm copy-pasting this, it's in the example that you should have in your computer that's called HMM. So far, what are we doing here is, this is the size of the FFT, the bin size. This is the window we're going to use. In this case, it's a Hanning window, same size. And then we define this hop size, which is half of the window in samples. And we are going to store that in a variable of type duration called hop size. Finally, we're very close to finish this example. We need the function to actually extract the feature. So I'm just gonna, again, copy paste that from the code you should have. This is a function definition in ChucK. As you can see, it's pretty similar to any C family language. Function, the return type is void in this case. The name of the function, here you can put the arguments if you want. This is an object-oriented language. This is not a functional language, so it's very different from Faust, but more similar to many of the languages you can see, like for common software. This is a while loop. This is a very different thing that happens only in ChucK. Most of the time, you always need to avoid this kind of thing. You never want a while true in a C++ code unless you are very conscious about what you're doing. But ChucK, this is a very ChucK construction, like a very ChucKian construction, because what we want to do is just keep analyzing this audio as far as we want. So the while true style, it's a very common construct in ChucK. Again, this is the wrong function for the analyzer. Then I'm just going through my dimensions. In this case, this could be, we don't need this. But I'm going to keep it because I'm going to change the analyzer in a bit. So for now, this could be just ignore, and we can use just this value here, and then the hop size. Okay, so now we Spork. Spork is a very ChucKian thing. ChucK is a very special language for controlling stuff. So when you're controlling music, you need polyphony, multi-threading, because every single instrument is going to be running in a different dimension in terms of triggers. So Spork is a very keyword, a very special keyword in the language to say, I want to run this function in a different, thread of the main one, just because I don't want this function to interrupt the rest of the code. So that's why we use this function that's called Spork tilde. That's Spork and then a tilde. We put the name of the function that we want to Spork, or just put in a different thread. And that's our feature extraction. And then we're going to just run the audio we have here. So the centroid of a sinusoid that's changing frequency. So let's play that. Okay, that's the centroid, that's the centroid, that's the centroid. You see there's 3 values here. The centroid for the 440 hertz of a sinusoid, it's this value. The centroid for the second frequency appears here. And then finally, there's a different centroid here. And that's it. With this code that you can just copy paste anywhere in any ChucK program, you can just switch your analyzer and it will give you whatever you want. So if you want RMS, the only thing you need to change is RMS. You change the analyzer and then you run it and it works. So RMS for the whole frequency is the same, which, okay. I'm going to print something to know. I'm just going to update here. Okay, what if we want to flux, a spectral flux? That's the spectral flux of this function. I don't know. This fancy statistical analysis that's called kurtosis should work. Yep. Again, 3 different values. let's say chroma, spectral chroma, whatever you want to use. It's pretty easy. Okay, that's the spectral chroma of this function. Okay, it's just running and it works. So that's the first part of our workshop. We learned how to do easy things, and now we learn how to analyze any audio. Questions? It depends. It depends on the analyzer, and that's why I just posted this reference in the help you have, because each one will give you different things. So, for example, Centroid, if you click Centroid, it will give you here some examples. Each example explains what the Centroid should give you. It should be a frequency in this case. But, for example, chroma, I don't know what's chroma or what's that for. So chroma features from a magnitude spectrum and gives you a vector of coefficients. Each coefficient, in this case, is the amount of one of the 12 tones in a tempered scale. So it will give you the amount of that note that's finding in the whole spectrum, for example. So the chroma will give you 12 values. Almost, I want to show you this because that will make sense. Let me just print a little bit of this, like just maybe 10 milliseconds. So chroma, for example, is not a frequency. Chroma is just a bunch of coefficients that tell you the amount of the presence of that note in the beep. So this is like C, C sharp, D, D sharp, E, F, F sharp, G, the amount of that note that it's finding. This is not precise, as you know. It depends on the window, it depends on the bins, because we are just analyzing, in this case, 1024, not the whole frequency spectrum as independent bins, but kind of gives you an approach of what's given, like, of the frequency content. So yeah, the reference it's trying to explain a little bit of what the extraction is doing. So this gives you some information of pitch data in the set of frequencies. And I was saying, you can just switch the analyzer with this code. This was very hard to do before, like ChucK 2016. It was more complicated, but now with these some new features, it's pretty easy. You just switch the analyzer, and then you have values, and then you do whatever you want with that. So far, so good? More questions? Okay, so this is pretty powerful. You can just analyze whatever you want. Let me analyze my microphone, for example. Instead of, if you want to analyze your microphone, you change ADC, which is the inverse of the DAC. In this case, is just hit play, and then, oh, sorry, but we need time to run, so let's run this for 2 seconds. Okay, so if you run this for 2 seconds, you should see some values. I think I'm not having values because I'm not connected. My microphone is unplugged. Yeah. My microphone is not plugged. Okay, I'm going to do that again. Not yet. Well, I think it's my microphone, but yours should be working too. I think when I unplugged the example I did before, I just unplugged everything from the mic. But yeah, like you can plug here whatever you want. Like it could be like a sample, for example, like a musicals excerpt or anything. So in that case, you will upload a sound buffer. I'm not going to do this, but I'm just going to show you. So that's a sound buffer, and that would be analyzing any audio you want to analyze. Okay, so let's just keep the sinusoidal thing. Okay, I'm going to keep that for now. So again, we did a very simple program. We learned a little bit how to write ChucK. Then we do this feature extraction. This code will work with everything. Actually, I think we're going to make this a class because it will make more sense because now it's the same code multiple times. So we're going to go back to our example code, and that was the first part of this example code that says HMM. We just go from the top to this part. Now I'm going to explain the operation overload because that's one of the new features of the language, which I think is very fun to play with. I'm going to remove this. So operator overload. What's that? Like if you do this in ChucK, let's say you want to print what's 2 plus 2, and you run. As expected, you have 4, which makes sense. So this operator, it's just doing what we are expecting this to do, but there are more abstract representations of this kind of operator because what does it mean if we want something like a vector like this plus a vector like this? Like there are possibilities. Like this could be element-wise addition, or it could be just a concatenation. So it's ambiguous. So that's why the language itself doesn't have a description of this kind of operation. But maybe you want to use this kind of stuff for your own cases. Because in my case, when this kind of thing is very useful because I work with melodies. And a melody is a vector of numbers, MIDI numbers. MIDI numbers are just an abstract representation of a note that goes from 0 to 127. Middle C is 60. Middle G is 67. Middle D is 62. So if you want to concatenate one measure plus another measure plus another measure, this makes a lot of sense. And so we need to define this operation because if you hit right now play, like this makes no sense to the language. You see? Error cannot perform this on object references. But we can define it. And that's one of the cool features, one of the cool new features of ChucK. So we need to do this operator overloading, which is almost just a function. So we create a new function. It could be a function. But in this case, we're going to say this is going to return another vector. And then we do this operator word. We're going to overload an operator, and in this case, we're going to overload this one. This is again in the same example. So if you just need to copy paste, you can just go here, go there. So I'm going to overload this on 2 vectors of integers. Let's call P, and it's a vector called P, and it's Q. Okay, so now I need to define what's going to happen with these two vectors. So let's say I want to make a concatenation. So what I'm going to do is, there are multiple ways of doing this, but I'm just going to copy paste the code you have in your example, which is this little function here. No, not this one, this one. Okay, so I'm creating a new vector. This is not entirely necessary, but I'm just using it like this so you can understand what I'm doing. This is the vector I'm going to return as part of this operation. And then I'm just going to add all the content in this vector, that's called P, to this vector. And after that, I'm going to add all the content of this vector into the same vector, which is called Q. And then I'm going to return this value. So now if I run it, now it's not now in theory we have an object here. You see, this is an object. So the operation is working. And I'm going to try to print that out. So let's create, this is also a new feature. We created this new auto type. Let's call it I. And I'm going to take this out of here. Okay, so I'm going to say this, whatever that is, it's going to go into, this is a new operator that's going to be used just for object assignment, like erase in this case. And I'm going to, actually it's not necessary. I think we can just do this. Yeah, it should work. This should work. Okay, so now I'm going to print, yeah, we have the values. So what's happening is we are concatenating a melody in this case. So we have a measure. I'm just talking like in abstract, the way I was explaining this morning. So let's say this is measure 1, and it has these 2 notes. This is measure 2, and it has these 2 notes. And when I do this operator now, it's giving me a vector that contains the concatenation of 1 and 2. But the beautiful thing is, like, you just described this for 2 arrays or vectors, but you can do it on 3 or 4 or anything, because this will just go one by one. So let's do another one, like 60 and 62, whatever that is. And you hit play, and it works. You see, 10, 1, 2, 8, 60, 62. So this is the kind of stuff that we added to the language because we are dealing a lot with AI. These simple algorithms I show you, more machine learning stuff that AI will say, to be honest. Like to use the more honest word. But we are dealing in a more symbolic layer or dimension. So that's why we are using this kind of operation right now. So far so good. This is a very new construct in ChucK language. This is also very powerful for like creating sequences, as the one I show you in the example in the morning. So this could be like a concatenation of a sequence or a Markov chain of triggers, for example. Okay, so this is like a for each loop. This is a C++ style for each loop. So for everything in this thing, print this thing. We also have the classical for loop if you prefer that one, but this is a new one, so I'm just showing you because I'm showing you the whole new stuff. Okay, so far so good. We can do this with any operator, so you can just create different operators. Like for example, the one I have here as an example. I'm just going to copy paste it. This operator is like like the negation operator. So I'm just gonna, if you do something like like this, let me do this. Same example. If you have false and you print false, you have false. So 0 is false. And then if you do this, makes sense because then, oh, sorry. What is here? What did I do? Okay, yeah. So, like, the negation of false is true. It's working. It's 1. But then, if you want to do this on a vector, what does that mean? It makes no sense as a definition, but it makes a lot of sense if you're doing triggers, for example, because you're not dealing with actual vector math or linear algebra. What you do is using this type of construct to store data. So in this case, this doesn't make sense, but with this definition here, what's going to happen is, let me show you. If I just put here this, and then I print. Okay, I need to. Okay, so let's see so let's compare the original vector with the new vector that was operated. So we have 1, 0, 1, 0, 1, 0, 1, 1, and the negation of that one is something that makes sense because it's like negating every element wise. So it's like 0, 1, 0, 1, 0, 1, 0, 0. And again, this is very useful when we are dealing with more abstract or more symbolic representation of music, because music behaves in this way. It's not linear algebra, it's a different type of thing that in this case works as a vector, but is not actually a vector in the sense of the mathematical sense of a vector. So we're not dealing with this as a thing that has to be closed on addition and multiplication as an algebraic group. We don't care. This is just a collection of triggers that we are using for triggering samples. So in this case, this operator makes sense. So this is the second part of the workshop. Now we know how to overload operators. It's a very new, cool stuff and cool feature in the new ChucK. So again, I'm going to stop here and questions. Good so far? Okay, so let's continue with the example. So we already made the feature extraction. We already did the operator overloading. Now I'm going to jump this part, but you have it there. This will not work on web ChucK because this is a chugging. It's going to be there like in a month, but not yet. So this is the new Chuggle, which is OpenGL inside ChucK. And just to be very fast with this, this is a new, this paradigm, like we're switching the whole thing. The graphics are dependent of the audio, contrary to every other language that deals with graphics. Most of the time, the graphics are running, and you sacrifice samples because of the graphic part. But here, we're trying to guarantee that every sample that you calculate is going to be out of the DAC.
Is ChucK already in the ChucK or must be downloaded separately from the...
Yes, if you go to the GitHub,
Oh, Spencer, no?
yeah, that's there. I show you this GitHub. Okay, so here's the link for the Chuggle. It's a chugging, so it needs to be needs to be installed. Here are the installation instructions. It's not very hard to install. If you have a Mac or a Windows, let's say you just go to the latest one, and there's the Windows. You just copy paste this into the ChucK folder, and it will work. Same for Mac. You just copy paste this into the ChucK folder. That should be in Preferences mini article, and then they will show you where's that. And for Linux, you should know how to compile from the GitHub repo. So there's no binary. You just go to GitHub and compile. Okay, so this is going to be fast. You have the example there, and also you have these two other classes here. This one that's called shader tools, and this one that's called shader type. I'm showing you that just because you're going to keep this code, and maybe you want to keep playing with this. So let me show you something pretty quickly. So I'm just going to comment this part here and see if this works. Looks like I deleted something from here. Okay, so this is just for a reference. This is 138. Where it is? Okay, this part.
What is the ChucK folder?
It depends on your computer, but if you go to mini article preferences, one of the windows will say chuggins. You click there and you will see there's a path. You just copy paste everything in that path and it should work. In case anyone or someone wants to see how that works, I'm showing you like this very fast. What's wrong? I think I did. Let me do a ChucK improve. Okay, so in case someone wants to run that, you need to run in this order these files. The first one you need to run is this one. It's just the definition of a type. So you run this, you load this one in the mini article and you run it. Then you go to shader tools, you run it. Finally, you run the ChucK code you want to run. This is just some helper functions for doing shaders. You can see this is just OpenGL code. So this is just helper tools. But yeah, I'm not going to stick here because then we're not going to see the HMM, which is the final stage of our presentation. So this code is going to stay there for your reference. If you need help with this, I can help you run ChucK, which is very nice because you can have pretty precise graphic designs because ChucK is very good for that. Contrary to OpenGL, which is very complicated to make loops and all the stuff. So I'm just going to leave that there. We're not going to talk about that. We're going to jump into the final stage here, which are the Markov models, the Markov chains, which is the last part of the example you have. Okay, so There's a lot of code here, and I'm gonna try to go fast through it because it's a lot, but I think you can catch the idea. So let me just, okay, so the first thing in here where they say chai, mix it with some ChucK, the first thing here is just a synchronization time, so you can have like triggers at the same time. This is the BPM, 130 BPMs per second. This is the, we'll say the note, or the subdivision. In this case, is subdividing each beat by 2. So that's mean like 8 notes, or so quarter notes. These are quarter notes. These are 8 notes. If you subdivide more, you have 16 notes, etc. This is the way you upload samples, audio samples. So I already say this. This is a sound buffer. You give a name, then you connect this to the DAC. I'm uploading 6 different audio samples here. This is for setting the gain of one of them that's very noisy. This one. This is the way to change the gain of the whole program. It was just because when I was doing the presentation this morning, Roman said that it could blow up, so I just put it like this. This is the way you give the path where the sample is. So everything is in a folder called samples, you see. Samples, and this is the name of the audio sample. This is the ChucK construction for saying in this directory, in the same directory where this file is, and then read that file. So it's doing that 6 times. This line here is just because when you read the sample, ChucK just want to play it when you run time. So this line is just saying, go to the end of the, like put the playhead at the end of the sample. So it will not play because it's going to be at the end. Okay, so now the interesting part. We are going to create some HMMs. HMM stands for Hidden Markov Model, which is a very simple stuff. It's just you feed a sequence into this Hidden Markov model. You set some weights, like, and you set some initial conditions. You set some emission conditions, and then you have infinite amount of different sequences that are related to the specifications you gave to the model. So I'm creating 4 of those. I'm creating 4 vectors, 4 vectors of size 8. Because if you remember the example I showed you this morning, it was an array of 6 by 8, like the sequencer. I created 4 because I'm creating just 4 HMMs, and then 2 of the instruments are hard-coded, like here. So this instrument is going to play the same rhythm every time. This instrument is going to play the same rhythm every time. In these 4 other instruments are going to play the Markov chains that are going to be creating new rhythms every time, depending on what you put as initial conditions. Okay, so this is my initial sequence, is the sequence I'm training my model. If you remember, I was talking about tiny models or small models or small mindsets. This is what I mean. The data here is just 18 numbers. So the sequence is a sequence of 16 numbers, pretty short, pretty manageable, and it's related to the way the kick drum or the bass drum in techno will sound, like boom, 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 boom. So this sequence, it's a pretty easy, predefined sequence of triggers in many of the electronic dance music. So I'm gonna train this model using this sequence, then I'm going to train another model using the same sequence but inverted. And I explained that in my morning talk. What happens with the hi-hat in the techno or electronic music, if you hit a kick, and then you have a hi-hat in the other, in the beat, upbeat, beat, like that. So you have boom, spoonch, 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 boom, 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 spoonch, spoonch. So that's why I created this operator in this case. This is a sequence, a different sequence for another hi-hat. It could be anything, it could be any long. So these Markov models will just work with any sequence you gave. The more information, the more precise. So if you, right now it's 16, but if you just copy paste this like 20 times, the model is just going to give you the same sequence every time because it's just going to understand that you want the same sequence multiple times. But with less information, it's less precise, but that's what I want because I want this thing to have variety, to sound different, because I'm using it as a generative kind of, like a generator of rhythms. So this also is hard-coded. It's just a vector of triggers. If you want to know what are these numbers and what else can you do with the Markov hidden model, you can just go here, AI tools, you go to HMM, and then you see that HMM has these three functions. You can generate something using the length of the sequence you want to generate, and this is the output vector you want to copy the output. You can load a model using the initial conditions, the transition matrix, and the emission matrix. This is more precise. This is just saying to the model, I want this sequence of things to happen with these weights. I want to start with this specific sequence. I want to go to this sequence. And then there's a function that's called train. That gives you the amount of states you want, the number of emissions you want of the model, and the observations you want to train the model in. So finally, this is very easy. And I was saying this is more, it's a very will not say AI stuff, it's a Markov chain that it's pretty simple to understand conceptually. And finally, I'm about to finish. So finally, we just go and put everything into a player. This player is just a while through loop, and then a for loop that's going through the vector. If the vector is a number 1, it will play the buffer for this amount of time. If the if the trigger array has a 0, it will just let pass time. That means plays if it has a 1, don't play if it has a 0. That's the only thing it sets here. I created 2 functions of those because this one is for the ones that are using Markov chains. This is the one for the ones that are not using Markov chains. And we already saw this. This is just multi-threading. So we are putting this 6 function in synchronization, one on top of the other. Each one is running at this time with this instrument. And finally, we just have a while through loop to just let pass time. And you already saw this example in the morning. This was the example I showed you in the morning. If you just want to run it, you can just need to close right now. Right now. Okay, so I'm going to close now, but you already saw this example. If you want to run it, you need to upload your samples to ChucK. I'm just going to show quickly that, and then I'm going to finish because Roman is already here standing. Okay, so if you want to run this in ChucK, you need to upload your files here, and you can upload your web files here. And then you just copy paste the part of the Markov models that's here, down, this part. And it will give you the same result I show you in the morning. It's this sequencer that's triggering new rhythms every time using this Markov chain as a source, which is great for live coding because that means you just need to type one sequence, like I want reggae, you give reggae, like the main reggae sequence, and then it will give you a lot of variations just based on the information you provide, the weights of the Markov hidden model. And that's it. Just to finish, there's another example that uses Wikinator. If you want to see, Wikinator is a very popular tool. I already saw that. So you can just go here and check it. And there's another example here that uses Wikinator plus an FM synthesizer plus your mouse, which is almost the same example that Miller was explaining us. This is the training set. You see, there's just one array, one result, one array, input, output, input, output, input, output. And then this thing with a multi-layer perceptron is just going to give us a very sketchy but good enough interpolation between those values. And I think that covers all the things you have there. And you know where to contact me. You know where I live. Most of you know where I work. So thank you.